Did anybody watch the recording?
I was not able to.
The first,
Huh?
first 15 minutes of it.
Okay. Did you watch the recording?
I got like halfway through it.
Cadence?
No.
When it was posted, I was working on some stuff on the house today.
So you might need to go back and watch the rest of that. I guess I'm gonna have to go back myself and see where I left off at the end of the video, because I had to shut my computer down last night. So you probably want to put that in the basket so I don't lose it. Do you need a stapler? Acid-base equilibrium, part 2. So exercise 9. Did I get exercise 9 done, or is that where I? Apparently I left off at exercise 9. Okay, so this should be somewhat of a review of acids and bases. We've talked about those. Exercise 9. Okay, so calculating the pH and POH. So just kind of a recap from yesterday. We had gone through, I think I gave you these for like homework. I think that's what I did at the end. We went through this one, and then I said, so I think I went through exercise 6 on the video, and then I said go through and do the other ones as homework. Okay, so we'll do those. We'll go through those. You were also supposed to be doing some stuff in that packet as well. The answer key, the first day I posted the packet, the answer key was posted there. I'll have to post the answer key for this one. I'm not sure how far we're going to get. We will not get to this packet today, but we may get to it on Monday, and so I want you to have it available. Okay, sorry about that.
Wait, Lucky, where are we at?
You are in the notes packet on page 9.
I know we don't have to eat.
Do you see page numbers down at the bottom here?
Yeah.
That's this one. That's the front of the one.
Okay, so when we calculated this, this was POH here. Or if we do a negative log of this value, it's going to give us the POH. And if we subtract that value then from 14, it's going to give us the pH. And that's how they were able to determine that it was a basic solution. Here, again, if we take this, if we do negative log of this, that'll give us the POH. From the POH, then we subtract from 14. And that'll give us the pH here. And then here, when we do this, we calculate that out. It gives us 1 times 10 to the negative 15 for our OH concentration, and this would end up being acidic. pH is 0. It actually comes out to be -1, but we usually don't have a negative pH, so we would just write it down as 0. Okay. So here you were asked to calculate the pH and POH for this one. So you should have your calculators out practicing how to do this. I'm thinking that we did this first semester, but I could be wrong. All right, So I'm going to take my calculator. I'm going to take the negative log of this value. So take the negative log of 1 times 10 to the negative 3. And you should end up with 3. So the POH equals 3. So then your pH, we subtract 3 from 14, should be 11. Are you able to get that on your calculator? If you take the negative log of the OH concentration, that will give you your POH. So negative log button, and then you type this in. What?
I don't know where the negative log button is.
Well, you have to hit the negative button, and then hit the log button, and then type in this, which would be 1 second EE negative again, and then 3 equals, and you should get 3 kicked back as your answer. That's your POH. Your POH plus your pH equal 14. So if I know this, I subtract this from 14, I get 11. Take the negative log of 1. That will give you your pH value here. And then you have to calculate your POH. You end up with 0 for your pH, so your POH would be 14. 14 minus 0 is 14. Okay? So this should be pretty simple for you to be able to do. All right. The next one, we're calculating blood. The pH is measured at 7.41. They want you to calculate the pH, the hydroxide concentration, and the hydronium concentration. So POH then, if we take 7.41 from 14, we would end up with 6.59. Okay. Now, if I have the pH, they said was 7.41. If I do 10 to the negative 7.41, that will give me my H plus concentration. And there you should end up with 3.8. Well, I guess it would be 0.8. Yeah, 89. I guess it's 2 sig figs times 10 to the negative 8. And that is a molarity. So you should have a capital M behind it. Okay. And then if we have this value, this then we know that 1 times 10 to the negative 14 equals our hydroxide concentration and our hydronium concentration. So I have this value. I now have this value. I can kick that up here, so I can solve it this way. Or I could also take 10 to the negative 6.59. I should come up with the same answer either way. Okay, so there's 2 ways that you can solve for the OH concentration there. Make sense? All right. pH of strong acids then. So we're going to calculate the pH of this nitric acid. When we're dealing with this nitric acid, we start with nitric acid, we add water in, and this goes completely over to here. We end up with hydrogen ions, and we end up with NO3 minus ions. Okay, it's complete transformation. bit of this changes into this stuff. So if we have this molarity to start with here, this is eventually going to go down to nothing, okay, to where we have nothing here for our E. Well, we don't have an equilibrium, but after. So this would actually be BCA table. And everything's going to shift over to here. So this would end up being 0.1 molar, and this would end up being 0.1 molar. So if we know that our molarity here is 0.1, that's going to be our molarity for our acid. Okay, they wanted a pH then, so if we do negative log of 0.1, our pH is 1. Does that make sense with this? What's going on there? Because things are going to change when we get to weak acids and bases. Not everything goes over then. Anybody not understand what I just did there? You don't understand, or you don't have questions? You're good? Okay. All right. The next one's done the same way. They want to calculate the pH of this molarity, hydrochloric. So we would just, since all of this is going to change into hydrogen ions, and then there would be chlorine for the next one, but all of this is going to change in. All we have to do is take the negative log of this, and that's going to give us a pH value. So our pH there would end up being what is going on? Okay. All right. So our pH value would end up being 10 for that one. Are you able to get that in your calculator? All right. So the same idea holds true here when we're dealing with strong bases. When we take this NaOH, all of this amount, so 5 times 10 to the negative 2, all of that amount is going to go over here and become ions. So all of that is going to change into where we don't have any of this left. We started with 0 of these. This is going to become 5 times 10 to the minus 2 and 5 times 10 to the minus 2. So if this is our concentration of OH, we just take negative log of that. So the OH concentration equals 5 times 10 to the minus 2 molarity. If we take the negative log of that value, that's going to give us our POH, okay, because we had OH here. It's going to give us POH. So I end up getting 1.30, and if I take that from 14, I end up with this for my value. So that's just a little bit of a summary of what we did yesterday. Okay, questions about strong acids, strong bases? Those should be a review of last year. We touched on that a little bit, very, very briefly at the end of last year. But all of those formulas, everything are on the back side of your periodic table formula sheets, that sort of thing. Okay. All right. Now we get to the fun stuff. We're coming back into these ice tables again that we had last chapter. And we're kind of bringing together this idea, this notion of these acids and bases, and bringing them together with equilibrium. So this is acid-base equilibrium. That is truly what this unit is about. And then next week, at some point, I think next week when you come back to me, I'm going to try to have a lab ready for you where you do an acid-base titration, since you never got to do one of those last year. So you really need to have some experience doing that. And then we will get into the fun stuff called buffers. Buffers are one of my most dreaded units, although they've gotten much better over the years, but it's not my favorite topic.
Don't say that now before we get to it.
Well, I'm just warning you that it is a level of frustration for me. So I try to gut through it and I try to explain it to you, but I sometimes get frustrated and have to quit for the day and come back to it the next day. So just realize that that happens sometimes with me, because you know how I am. If things don't go exactly the way I planned, I kind of have to regroup and start over the next day. So, all right, so we are going to have to go back to these rice tables, because when we're doing these, and this should have an arrow here, I'm sorry. When we're doing these, we're taking an acid and we're breaking it down. But remember, this is not a complete breakdown. Most of the material stays over on this side. So when they give you a molarity, this is the molarity of the weak acid that you're working with. They're going to tell you that. So that's going to be your initial amount. You're going to lose X, and then this side is going to gain X. But remember, if we are dealing with, equilibrium where we have smaller, this is less than 100 difference, we still have to use the quadratic equation. They're not going to make you on the test. Most of the time with anything that we do, we're going to be able to ignore this X. Now this example here, they had to use it, but that's ugly. Most of the time we will be able to do it and we won't need that dreaded quadratic equation, and you will never need it on your exam, okay? So most of the time we'll be able to ignore it. You just have to document that you ignored it. All right, so here we go. Here's the fun stuff. See, I don't dread this. This is not bad. We can do these. Here we go. All right. So typically I do what she tells us to do up here. I don't necessarily write out all of this every time. All of these formulas, subscripts, all of that stuff. Okay. What I do, where does she do this up here? Trying to find it. Do you think I can? Yeah, here it is. It's coming up. This is what I do. Okay. I do this. I take my acid, my hydrogen with my anion. So hydrogen anion, add water to it, break it down into my H plus and my acid. Okay. This anion is coming off here. Then I don't have to mess with writing all those subscripts and all that garbage out. I save myself a considerable amount of time by doing that. Okay. So my equation essentially is HA plus water yields, and this is equilibrium, and this is a weak acid, so it's going to go both directions. It's going to give me my hydrogen ion, and it's going to give me this. Okay. Now, could I write that out? Sure. Okay. But I've just saved myself a lot of time trying to, okay, well, I've got this. I'm going to write down HOCl plus water. I'm going to have the hydrogen. Then I've got to figure that out and put that down here. If I just do this blanket generic one, it suffices. Okay. And they don't mind that. They're okay with that on the exam. So I look to see what my initial molarity is. This is my initial molarity. So that's going to be here, 0.1. I ignore my water. Water doesn't get factored in. Then my H here, when I started out, I didn't have any of these. Here, I'm going to minus X. So this is going to be 0.1 minus X. And then I'm going to add X here and here. So this is my materials at equilibrium. Okay. Now, my Ka value here, and I want to make sure that this is Ka, because sometimes they will give you a Kb, but if you have hydrogen here, you need a Ka. All right. Remember that Kw equals Ka times Kb. So if this equals this, and you know one of these, this is always a constant, 1 times 10 to the negative 14. So if you know Kb, you can get Ka. Okay, that's at 25 degrees Celsius, but all your problems are going to be, so don't worry about it. Okay, so but nevertheless, we had a Ka. That's what we need for this, so we're good. So I have Ka here. Because this is on the order greater than 100 times different between this order and this order, I can ignore this. I just need to document it. And all I have to do is say ignore. I just have to report back to them that I recognize that this can be ignored. Okay, I don't need to go into any grave explanation for it. I don't need to show them math. I just need to show them that, yeah, I checked this and we're good. I can ignore that. Does that make sense? All right. So now I'm going to set up my Ka value. I'm going to have x squared, because x times x is x squared, over 0.1. And they gave me the Ka value here, so I just plug that in, and then we can chug, right? Plug and chug. So 3.5 times 10 to the minus 8 times 0.1 is going to equal x squared. So then x, we just multiply those together, take the square root. 3.5 negative 8 times 0.1 equals. Then I'm going to take the square root of that. And I end up with 5.92 times 10 to the negative 5. That equals my hydrogen or my hydronium ion concentration. So that is a molarity. Okay. But that's not what they wanted to know. They wanted to know pH, didn't they? So we always need to go back and check our problem and see what they were actually asking for. So if we want to find pH of this, what do? Negative log of this will give me the pH of 4.23. That's doable, right? Not so bad, yeah? All right, next one. Let's see here. We have a mixture here. We have hydrocyanic acid, and we have nitrous acid. And they've given us the respective Ka values. They want us to calculate the concentration of cyanide at equilibrium. So I need to do a couple different ice tables here. Okay. The first ice table I'm going to do for this one, I'm going to have my HCN or HA if you want. I'm just going to ignore the water here because it doesn't really matter. This is going to give me HA. And you might want to, give this a heading of CN minus just to keep your kind of, things straight. I'm going to start out with a 1 here. And I'm going to end up with minusing x. And so this will be 1 minus x. This will end up being x. And this will end up being x. So they've given me the Ka for this one. It's 6.2 times 10 to the minus 10. I can ignore this. I just need to document that I can ignore it. Because this is a very large magnitude difference between that and 1. So easily ignored. That is then going to be x squared over what? 1. Okay, do the math, figure that out. And for this one, that's going to equal my hydrogen ion concentration, and that's going to equal 2.5 times 10 to the negative 1, I believe. -5. Did I say -5? I don't know what I said. I think I said -1, but I meant -5. This is what I meant. All right. So I have it for that one. Now I need to do the same thing, but this time I need to do it for this using this Ka value. So set up your ice table for your HNO2 and see if you can come up with the concentration that you need for that one. So tell me what your H plus concentration is going to be for this guy. All right, were you able to come up with 0.0447 molarity here? Anybody not able to get that number? Okay, so if we had our HA here, our H plus A minus, this is going to be our, we had 5 here, 0, 0, minus X plus X plus X. So 5 minus X and X and X. Okay. So when I solve for this, I'm going to end up with 4.0 times 10 to the minus 4 equals X squared over 5. Did you get that? Okay. You multiply this times 5. And then take the square root of it. This is the number you should get. Did you type this in correctly? Did you go 4 and then hit second E, -4?
Nope, I did -5.
Okay, that might do her. Okay, so once you have that, this is what you end up with your answer. Okay, then we need to figure out, they want to know, so calculate the pH of the solution that contains this, and then also calculate the concentration of cyanide in this solution at equilibrium. Okay, so if we take our concentrations here of these two things and we add them together, that's going to give us the concentration of H plus. So add these two things together, and that's going to give us our overall H plus concentration. Okay. When you add them together, you essentially get this, because this was such a small magnitude value compared to this. You end up with 0.0447 molar. And then if we take the negative log of this, your pH should end up being 1.35. So then, if we want to figure out our concentration of cyanide here, okay, Remember, when we put this together, our cyanide ended up being this guy right here. So this is our cyanide right here. Okay? So if I want to figure out my concentration of my cyanide, I can take now my values. I can take my Ka for cyanide, and I can take my H plus concentration here, which we are going to get and bring in from right here. I can take my A minus, that's what I'm solving for now. This is what I'm solving for. And I'm going to divide that by my HA. Okay? So if I want to rearrange this equation and solve for A minus, I'm going to multiply this to both sides. So cancel it over here and bring it over here. So then I would have H plus times A minus equaling Ka times HA. I want to isolate this guy still. This is what I'm still solving for. So what do I have to do? I have to divide both sides by H plus. So A minus equals Ka times HA over H plus. Oh, algebra. Sweet algebra.
Sorry to interrupt. I was just wondering, on here it's asking for the formula of hydrochloric acid. Are we supposed to come up with that?
You should know how to write hydrochloric acid, yeah?
Yeah, I do. I was just making sure that it wasn't like. Never mind.
Okay. All right. So I'm solving for A minus here. I'm solving for this cyanide concentration here. I have all of the values for this. Okay. My A minus is here. My Ka was given up here, so I just plug that number in, 6.2 times 10 to the minus 10. Then my, so that's my Ka. My Ha then was 1. They gave that to me right here. See that? Right there. So I'm going to plug that in. And then I just divide by this value. So 0.0447, this value that we added together down here. I'm grabbing that and I'm bringing it in right to here. All right. And when I do that, I end up with this. You should end up with that for your answer then. Boy, wasn't that fun? You enjoy that one? Good times, huh? All right, you ready for the next one? All right, exercise 13. Calculate the percent dissociation of acetic acid. Okay, in each case. So we have different cases here. Remember that our acetic acid, we're going to have kind of, oops, I need to get rid of that. Hold on. Back to my normal pen. Oh, this went really far down. Sometimes it does that. It just slides past. There we go. All right. Let's see how clean I can keep this one. I don't know. I just can't seem to keep my stuff clean. So my HA, my H plus, and my A minus. Okay. This is my A minus here. But did you see how much time I saved myself writing that out? Okay. In my first scenario, I'm going to start with 1 here. That's going to be 1 minus X. These are going to both be X's. If I can just skip to the E. Can I skip to the E? You're good with that? Okay. I can see that this order of magnitude is over 100 times different than this order of magnitude. Therefore, I can ignore this. I just need to document it. Okay. Then I can set up my situation here where I have 1.8 times 10 to the minus 5 equals x squared over 1. I can solve for x, which also equals my hydrogen ion concentration, and it equals my A minus concentration. And when I do the math for that, I end up with 0.0042 molar. That's not the answer, though. That's not what they asked for. All right, what they asked for was percent dissociation. They're asking for how much of this part came away from this whole. So we take part over whole times 100. And that's where they came up with this for the answer. So now see if you can take that and replicate that situation for B. So this was A. See if you can come up with B here. You done?
Just am I on the right track with it?
This is not hydrochloric, no. Hydro,
Okay,
there's no oxygen.
That's what I thought.
There's no oxygen in hydrochloric. You guys need more time on this one? Okay. Okay, good. Able to get that? Yes? Okay. All right, so the next one, lactic acid. So this is what builds up in your muscles that makes your muscles ache the next day, like after you've had a hard workout or something. All right, we've got a situation here where it's going to be 3.7% dissociation. They want us to calculate the Ka. So essentially what we're doing is we're doing this in reverse. Okay. So if I know that this is 3%, 3.7% disassociated, I'm going to take this value times 0.037. That's going to give me the molarity of my H plus concentration. So I end up with 0.0037 there. Yes? Okay. So then if I set up and I solve for Ka, Ka is going to equal, well, if I had this as an ice table, I guess I should back this train up, or I'm just going to do it over here. My HA, my H plus, my A minus, okay? This is going to be 0.1 minus what am I doing here? Yeah, 0.1 minus 0.0037. Good job. Yes, yes, very good. And then this would be 0.0037, and then this one would be 0.0037. All right, good job. Okay, so this is going to be 0.0037 squared. This is going to be 0.1 minus 0.0037. So when you do the math out on this, all you have to do is crunch that data. You should end up with the 1.4 times 10 to the minus 4. And I think that's a good place to stop for tonight. I'm going to find in your packet where that would leave us off in this packet, and I'll post on here where I expect you to be by Monday on that. Okay? All right. Sharing.
Next week is this, what week?
No.